Good morning, children. Today we'll discuss about infinitesimal rotations as vectors, angular velocity. Let us go with the presentation. Infinitesimal rotations as vectors, angular velocity. Here we will consider two cases here. First one, let us see a finite rotation, or if we consider any angular displacement which cannot be represented by vector. Why a rotation, or why an angular displacement, why a finite rotation or an angular displacement cannot be represented by a vector? Because the sum of two such rotations, one after the other, is not given by the parallelogram law of addition of vectors. Now let us see that one. And here let us consider a sphere, and here this is the origin O, and here we have a particle at a particular point P, and here when the particle P which moves from particle P to Q about the OR, that means here OR is fixed here, and here the particle P moves from P to Q about the 90 degrees, and after that again this particle from Q to R, again it moves a rotation of 90 degrees about a OP. That means here in the first case, when the point, if we consider a sphere, in the first case the point P moves from P to Q about the 90 degrees about by fixing the axis OR, and then the particle from it rotates from Q to R about the 90 degrees by keeping the fixed as OP. And here the particle from P to R, it moves here from P to Q and Q to R, and here from two times it travels. But if we consider from P to R, if it moves with an angle 90 degrees, and within one step the point, the P can be moved from P to R about OQ. But here if you consider this OQ, which is not in the case in the parallelogram here, so this OQ, it cannot be in the parallelogram which forms when the particle moves in the sphere from P to R. That's why here the finite rotation of angular displacement cannot be represented as vector here. That is the case. But if you consider here, that means here representation of infinitesimal rotation as vector, and here we have this is the point, particular point O, and here the particle moves. Here we have OR, and here we have when the particle moves from P to here. If we consider any particle on this surface, that means suppose let it be A. If it moves from A to B, and then by fixing the about the OR, that means here OR is fixed. That means if a point on this sphere, it moves from A to B about OR, and here when again this part from B to C about a fixed point OP, that means here a point on the sphere from A to B and B to C here, and that means here from A to B, here we are considering OR, and here from B to C, and we are considering here about OP directions, and here a single path here from A to C, that means along OQ. Along OQ, here we can observe here from A to C, that means in a single direction. Here we have from OQ, that means here this AC, it is a diagonal of this particular parallelogram formed. That's why here this is the representation of infinitesimal rotation as a vector. But here finite rotation cannot be represented as vector when the particle from P to R, when it moves here about the OQ, and this OQ, it does not contain in the diagonal of the parallelogram which is formed by the point by the rotation of P to R. That's why here finite rotation cannot be represented as vector, but this representation of infinitesimal rotation as we can as a vector because of this path which is the diagonal of the parallelogram which is formed in particular movement, in particular rotation. And already we have seen all this one, and here if you consider, okay, and now let us see if the rotations are already we have seen the figure 10.8 also we have seen, and this is the AC diagonal which is formed in the particular parallelogram already we have seen. And now see, so here now if d alpha is the infinitesimal rotation occurring between t and t plus dt times, then Instantaneous angular velocity omega of the digit body is defined by the rotation. And if you see here from this figure, and this is the figure infinitesimal rotation d alpha and angular velocity omega, which is equals to d alpha by dt. And here this is the infinitesimal rotation d alpha and angular velocity omega equals to d alpha by dt. And here this is the representation of linear velocity v, which is equals to omega cross r. And here this is point O, this is beta, this is r, and here we can see r plus dr, and this is r, and this is angle d alpha. This is the angle of infinitesimal rotation. Here this is angle of infinitesimal rotation. D alpha equals to omega dt, r omega equals to d alpha by dt. And here this is velocity. Here we can observe representation of linear velocity v equals to omega cross r. And by using this figure, so by using that, omega dt equals to d alpha, or omega equals to d alpha by dt. Here the vector omega is along the axis of the infinitesimal rotation. So the instantaneous linear velocity of a point at r relative to the origin O is given by v equals to omega cross r, where the magnitude of the instantaneous linear velocity is omega r sine beta. So this is about the infinitesimal rotations as a vectors. Thank you, children.